we moved on to looking at things that potentially might not be obviously evident from the ECG. So it turns out you can detect and predict future hypertension from an ECG. So if you put an ECG into a model and take its prediction and follow the patients up over 15 years, all retrospective data, you find that models can quite accurately pick up those at the highest risk of hypertension even before their blood pressure readings are abnormal. So clearly there's some subclinical changes that is being picked up on the ECG that the model can recognize. And if you look at traditional parameters, how to predict future hypertension, including age and sex and other parameters, AI-ECG seems to do a better job of doing that. What's more, AI-ECG seems to be able to pick up hypertension-related complications. So the same model can predict future cardiovascular death, heart failure, MIs, strokes, and CKD. So seems to be picking some signatures up of hypertension in the ECG even before its onset. And when we looked at the echocardiography, the model predictions are associated with things we recognize, like wall thickness and some early changes related to hypertension. What else can we do? So we can look at non-cardiovascular disease. So we looked at using ECG to predict things that are non-cardiac. And it turns out you can diagnose and predict future diabetes from the ECG. It's thought that glucose levels can affect electrophysiology, and there are changes that are recognized in diabetic patients. So again, if you take a single ECG and make a prediction of future diabetes, the highest risk group end up having a lot more diabetes in the deep red line here compared to the other quartiles. Understandably, the C-index for predicting non-cardiac disease is not as good as predicting cardiovascular disease. So the C-indices I showed yesterday for future heart failure, future complete heart blocks are sort of 0.8, 0.85. For non-cardiac disease, it's around 0.7. So not amazing, but you can use an ECG to predict future non-cardiac conditions like diabetes. And this whole, we talked about external validation earlier. You have to not overfit your model. And we looked at testing this in external cohorts. These models hold in their predictions both in healthy and sort of disease cohorts. And in terms of diabetes prediction, if you look at comparisons to the gold standard, which is the American Diabetes Association risk score that combines all of the measures above, AI-ECG outperforms it. So the green is AI-ECG, the risk score is in red. So having ECGs appears to be additive to our current existing tools to pick up patients at risk of diabetes. And it seems to work quite well in people with A1C levels that are normal. So even before you are pre-diabetic, the ECG contains signatures that would tell that someone will become diabetic in the future. And you might use that in creative ways. So you might use it and say, well, actually, you are at future risk. Maybe you should lose weight, go into an exercise program, things that might be preventative of future problems. And this is the external validation graph, very similar to the internal test set. So we heard earlier about exporting signals and XMLs versus PDFs. Almost all ECG models we've talked about so far are focused on using the actual raw signals. So you have to take the GE news system, export an XML format data, and then run your models on the voltage tracers. There are lots of situations, both in, for example, the UK and other low and middle income countries where digital infrastructure is not available. So those systems are not able to tap in to the benefit of AI-ECG models as they stand. So some of our work has been focused on using images as input rather than the actual raw signal, and we want to say, can we take the image rather than 12 independent leads to make the predictions? So what we've done is taken lots of PDFs, but also odd images that are photographed, that are partially pictured, scrumpled images, folded paper, and then train the model using suboptimal images rather than the clean GE Muse XML signal, and work out whether or not we could make similar predictions. So this was a different model. It was a 2D CNN rather than a one-dimensional CNN using 8Ds. So we trained that using lots of PDFs and lots of images to make a range of predictions, as you can see there. It turns out that actually the image models, depending on the task, can be comparable to the signal model. So if it's like using structural heart disease, for example, a reduced LVEF, the image models are close enough in terms of performance to the ECG digital signal models. You can see if you just use the PDF image, clearly you get a much better performance in a tight C-index. If you start using photographs that are poor quality, scrambled paper, you get a whole range of performance. But the message here is we can actually move beyond, if we wanted to, the raw digital signals, and models can actually be applied just to pictures of ECG. So if you work in a healthcare system where you don't have GEMUs and you don't have a digital ECG system, you could use an image model that might be equally powerful. And here are some saliency maps looking at what the model was looking at. We did a bit of an experiment. So for the mortality prediction, we wanted to say, if we take an image, what kind of resolution do you need to make an accurate prediction? So we took the high resolution PDF and slowly, in the same image, reduced the spatial resolution. And we were somewhat surprised that actually you don't get the drop in performance of the model until you really reduce the resolution. So even at this kind of resolution, you have a C-index of over 0.7. So there's something in this low resolution image that allows the model to make the prediction. And that's interesting because it's probably just looking at the amount of QRS and the QRS amplitude here. The more black you have on that paper, the better or worse it is. Even if you use, so it drops when it goes to that. But interestingly, I've got an image, even with a 1-to-1 pixel. So if you reduce the whole image into a single pixel, it still has a more than 0.5 C-index. So there's something about the grayscale and how much gray in that ECG that's telling you about risk. So I think that's to do with heart rate, so how many QRSs, how big the QRS, but the grayness in the grayscale with a single pixel is still informative and is not quite a toss of a coin. What else is new? So a completely different angle we've been doing is using machine learning for gene discovery. Traditionally, you can do gene discovery to work out what genes are important in the ECG by doing GWAS to PR interval, QRS, and QT. The limitation there is you have to do it to something you can measure. So you got to measure the PR interval and say what are the SNPs associated with a long or a short PR interval, and then you measure the QRS. You say what are the SNPs associated with a long and a short QRS, but it limits you to what you can measure. So with machine learning, what you can do is describe the ECG in many other ways beyond PR, QRS, and QT interval. So what we've done is to break down the ECG using, I showed this earlier, a variational autoencoder, where you take an ECG, put it through an architecture, and in the middle you get 20 features, and then you can decompress it. And what you can do then is to take this additional 20 features and run GWAS on them to find whether there are additional SNPs that are important in determining the ECG that were not picked up using traditional PR, QRS, and QT GWAS that we've done previously. Here's an example. So for this particular feature that was derived by the neural network, which you can see by eye, probably relates to the PR interval. It's picking up SCN10A, which we know is important in the AV node. So you can use that to discover genes. I want to finish off with a potential misuse of AI-ECG. I think AI in general can be misused, but AI-ECG can also be misused. And that's because the ECG, I think, is being viewed as a biometric. It's kind of like your fingerprint. So if you have someone's ECG, you have the unique signature of the electrical activation of their heart. And there are people who are thinking about using ECGs as a way to unlock your smartphone. So you have your fingerprint plus your ECG, and then in combination is probably more secure than just having a fingerprint. So we want to see whether this could be abused, and we trained a Siamese neural network to see whether you can recognize two ECGs are from the same person, to try and pick someone out using their ECG alone. It turns out that it's not bad. So if you take, we have 2 million triplets, so each triplet contains two ECGs from one person and one from someone else. It's pretty good, and for about 90% of the time, it picks out the two ECGs from the same person. So there's something about your ECG that is unique to you that AI models can pick out. And that's dangerous because we have a lot of large data sets with ECGs inside them that are linked to all kinds of sensitive information, like genetic code, like your entire medical history. And the concern is, can a motivated intruder with an ECG match you out of a big database and pick out all your information and know everything there is to know about you? So for this paper, we simulated this task, and we said, if you have a big data set of 10,000 individuals, and I knew you were in that data set, and I have your ECG, how can I pick you out? It should be a 1 in 10,000 chance, but can I pick you out accurately using an AI model? and we had some criteria of how we would do that. The scary thing is these things are unbelievably accurate. So if you had a data set of 100 individuals, it should be a 1 in 100 chance of picking you out of that data set. It gets it right about 80% of the time. If there's 20,000 ECGs and you want to pick that needle out of a haystack, and it should be 1 in 20,000, the model gets it right 40% of the time. So it's not amazing, but to go from 1 in 20,000 to 40% seems amazing. And if you add age and sex, so if I know Sonos in the database and I know she's female and her sort of rough age category, I can get quite good at picking her out from a big database and learn all about her medical history. So I think this is a lesson to us. The ASG has a lot of potential benefits, but it comes with some risks, and some of the risks come with privacy risks, given that the ECG itself is a biometric with unique signatures. But that's all I have to say in terms of the recent advancements. Thank you very much.